Okay, today we're going to develop what are called the Mach number relations. And we can develop relations between the Mach number and the static and stagnation properties. So in our discussion, we're going to assume isentropic flow and some constant Cp. Well, the specific heat will be at some average value. And there will be no heat transfer, so Q, obviously if it's isentropic, there'll be no heat transfer, Q equals 0. We're going to say there's no work, so there's no compressor or no turbine in the channel. And there's no change in elevation, so the elevation Z1 stays the same. So if we recall the energy equation, we have that Q plus H1 plus V1 squared plus GZ1 equals H2 plus V2 squared over plus GZ2 plus W. Well, obviously the W we said was equal to 0. The Q is equal to 0. Z1 equals Z2. So we're left with H1 plus V1 squared over 2 equals H2 plus V2 squared over 2. Now let's let V1 equal 0. So we're talking about in the stagnation region. So then H1 equals the stagnation enthalpy. Okay, so because GZ2, well, cancel that, and W went away, that means H0 now equals H2 plus V2 squared over 2. All right, I'm going to rewrite H, H0 minus H we could write as Cp T0 minus T for an ideal gas, and that's going to equal V squared over 2. Now notice I dropped the subscripts here because T, the 2 is just some arbitrary position, so it doesn't really matter, so we'll drop it. And we're going to solve this for T0. Now we've already done this once in a previous lecture. T0 is equal to T plus V squared over 2Cp, and then I'm going to divide by T so that we have the ratio of the stagnation pressure to the temperature is equal to 1 plus V squared over 2Cp/T. So we haven't done anything new yet here. If we take the definition of enthalpy, where H is U plus P over rho, which we've talked about before, if we have an ideal gas, then P over rho is equal to RT, so H is equal to U plus RT. Something to note here is that U is a function of T, and obviously RT is a function of T. So for an ideal gas, the enthalpy is a function of temperature only. We can look it up for any pressure, and that'll give us the correct, as long as we know the temperature, it'll give us the correct enthalpy. So if we take the derivative, dH is equal to du plus R dt, write this in terms of our specific heats, Cp dt equals Cv dt plus R dt. I've just rewritten the equation here, but we can cancel out the dt's, and we're left with Cp minus Cv equals R. And you would have learned this back in thermo, but this doesn't hurt to review it. We'll divide both sides by Cp. So we have Cp over Cp is minus Cv over Cp is equal to R over Cp. The ratio of the specific heat, Cp over Cv, is gamma, so we have 1 minus 1 over gamma equals R over Cp. And then we can solve for Cp, and we find that Cp is equal to gamma R over gamma minus 1. So I'm going to substitute that back into our expression for T0 over T. We get T0 over T is equal to 1 plus V squared times gamma minus 1 over 2 gamma RT. Well, remember, gamma RT is just equal to the speed of sound squared, so I put that over here. So we have, now we have a V squared over A squared, and you might remember that that is the Mach number squared. So we come out with an expression, the ratio of the stagnation to the temperature at any point in the flow, T0 over T, is equal to 1 minus gamma minus 1 over 2 times the Mach number squared. So we developed a relationship that tells us what the temperature is as long as we know what the Mach number is. Okay? Remember the isentropic relations that we learned back in a previous lecture? We had P0 over P is equal to T0 over T to the gamma over gamma minus 1. Rho 0 over rho equals T0 over T to the 1 minus gamma. So if I substitute that into the expression for temperature, I can get two additional Mach number relations. One where we relate the stagnation pressure to static pressure anywhere in the flow as long as we know the Mach number, and one where we can relate the ratio of the density, stagnation density to the local density given a Mach number. Okay, so I've rewritten those equations here to summarize it. So these last three boxed equations that I had up there are referred to, let's see, these are referred to as what we call the Mach number relations. So I've just summarized them here. These are the same three equations we had up there. And we use these a lot. We're going to use these in our next lecture. We're going to talk about converging nozzles, and then we're going to go to converging, diverging nozzles, and we're going to use these relationships over and over. And so I'll be referring to them as the Mach number relations. And then, if we take those equations and we set the Mach number equal to 1, we have what are called critical properties. Now, there's nothing's going to happen special where we call them critical. That's just a name that they're given, but they're called critical properties. That's where the Mach number equals 1. And where the Mach number equals 1, we denote it with an asterisk. So if we take the Mach number relations that we just had up there and we set the Mach number equal to 1, we get these three relations. So I've got T0 over T star now. So T star means that's the temperature where the Mach number equals 1. And if we plug in a Mach number of 1 into our relation, we end up with 1 plus gamma over 2. And if we do that for pressure, here I have P0 over P star. So we're talking about the critical pressure. That's where the Mach number equals 1 is equal to 1 plus gamma over 2 raised to the gamma over gamma minus 1. And then rho 0 over the critical density is equal to 1 plus gamma over 2 raised to the 1 over gamma minus 1. Now, I've drawn that on the diagram here. If the Mach number is 1 at the throat, and it doesn't have to be 1 at the throat, but if the Mach number is 1 at the throat, then we have critical conditions at the throat. And our diagram for our converging, diverging nozzle would look like this. So note I've written here, if M equals 1 at the throat, then right here at the throat, the point of minimum area, we have T star, rho star, or P star, and rho star. Those are the critical properties. Okay, there's no, if the conditions aren't right for having Mach number of 1 at the throat, then it would not be T star, P star, rho star. But we could still calculate it, but the Mach number has to be 1 at the throat. And we're going to talk later about what the conditions have to be in order to have a Mach number of 1 at the throat. And then, just to kind of give you a heads up for what's coming, if we have a Mach number of 1 at the throat, then downstream we could either have supersonic or subsonic conditions. Or we could have supersonic in part of the channel or duct, and then we could have a shock wave and then subsonic flow downstream for that. So we're going to talk about that in subsequent lectures, what happens downstream of this point here. Now, if we do have supersonic, or if we do have sonic flow here at the throat, Mach number of 1, then no matter what we do downstream does not affect upstream. the upstream will not know about anything downstream if we have a Mach number of 1, because anything that happens downstream has to be transmitted upstream at the speed of sound, and it reaches this barrier right here. It can't get through there because we have the speed of sound here. And if you're going at the speed of sound, then you stop right here. So nothing that happens downstream here makes its way upstream if we have a Mach number of 1 here at the throat. And that's all I have for this particular lecture. So thank you.